Okay, so this is the recording on uh, the reactions of alkynes, and so before we get into the reactions that they do, let's talk first about how we make alkynes. So let's say synthesis of alkynes. And so the easiest thing to do is to treat a dihaloalkane with base. So we'll just write treat a dihaloalkane with base. And it needs to be a strong base. So strong base for elimination. So how do we do this? Well, we can get to a dihaloalkane from, for instance, brominating something. So for instance, if we take an alkene, if you remember from the reactions of alkenes, we can treat this with Br2, and we end up with our dihaloalkane. And you should remember this from the lab where we prepared acetylene. And so now the next thing that you can do to prepare the alkyne is treat this with a strong base. So we treat this, say, with potassium hydroxide. And we force this to undergo an elimination reaction. And so what you can see now, the thing that you need to note is that we're going to eliminate this hydrogen right here, right? And the electrons are going to go to form this bond at the same time, kicking this one out. Okay, so notice that you're not going to go from here down to this one. You're going to go, this carbon, you're going to go from here to in between this bond. So the arrow should look something like this, where you are going towards the hydrogen, and these electrons are now going to move in to form this new bond between here, and then that forces these guys to come out to the halogen. And so this gives you your first eliminated product. And the next thing that can happen is if you have more base. So we have more of our OH minus from our potassium hydroxide that we used. And we'll finish this with the second elimination. Again, going in between the bond here and kicking this out. And this now gives us our alkyne. Now notice also that there is a carbon right here. Sometimes I see people where they don't realize that this is the actual carbon. It is right there. Okay, that's where the carbon is. So that is how you end up making an alkyne, or it's probably the most straightforward way to make an alkyne. Is through the elimination of a dihaloalkane. Or you can start if you have something, for instance, if you have something that is already in this fashion, you can do another elimination on it here, and this will also give you an alkyne. alkynes. And so we're going to, in this case, we're going to look at the addition of HX. So I'll just say addition of HX. So this could be HCl, HBr, HI, anything like that. Typically the most common ones you'll see are HCl and HBr. So let's look at the addition of HBr. So I'm just going to draw a simple alkyne. So here's our simple alkyne, and we're going to add to this HBr. And of course, the very first step that's going to happen is we notice that here is our center of electron density right here. And this is going to come over here and grab our electrophile, which is the hydrogen on HBr. And it's going to force the electrons to go from the bond in here to the bromine. And so this gives us our new product, or our intermediate in this case, which looks like this. And now we have a carbocation here. Now, notice that in this case I've drawn the carbocation that is on this carbon. So this carbon is what we call a secondary vinylic carbocation. And it's vinylic because it is on the double bond. So you can see right here that it is on the double bond. If it was on this one would be what we call a primary vinylic. And it's not stable, so it doesn't form. Okay, so now you can see that we're going to end up getting our Br minus that's going to attack at this point on this carbon, not on this carbon. So the more highly substituted carbon is the one that forms. And so I'm just going to draw right down here. I'm going to draw my Br minus and have this guy going in and attacking this carbocation. And this gives us our initial product. We'll put the Br right here and a double bond. And there we go. And so this can happen again, and we can treat this with another equivalent of HBr. And again, our center of electron density is this guy right here where the double bond is, and this can come down there, and we end up now forming this intermediate that has now this carbocation right here. And again, another molecule of Br minus that we just generated can come in and is going to attack that carbocation. And so we end up here with our product, where we have two Brs now added, and we've also added two hydrogens. Remember, we had one that was already there, and so we end up with this type of addition. So the key points to take away from this are that the primary vinylic carbocation doesn't form. And so, therefore, the more highly substituted carbon is the one that gets the carbocation. So more substituted carbon gets the carbocation. Okay, now we can talk about the next set of reactions for alkynes, and this is what we call hydration, or adding water across an alkyne. So we can just say here hydration of alkynes. And so the first one that we're going to talk about is when we use mercury 2 as a catalyst. So we're going to use mercury 2 as a catalyst. Oops. And so the actual reagent that we're going to use is mercury sulfate, so HgSO4. This one is, of course, this is a Lewis acid catalyst. And so the other hallmark of this reaction is that we're going to end up getting what we call, of course, Markovnikov regiochemistry. So we get Markov, if I could spell here, Markovnikov regiochemistry. So what does that mean? That means in this case that the OH is going to add to the more highly substituted carbon. Okay. So let's look at what's going to happen here. So let's just take an example. We'll use our same alkyne that we used for the last reaction. And so if we start off with CH3 and then put in our alkyne right here. And we're going to treat this first with mercury sulfate. And this is going to be a mixture of sulfuric acid and water. Right, so we've got a lot of water here now. And so we'll just have sulfuric acid and water. That's right here. And so remember that mercury here has a 2 plus charge, and then this, of course, our sulfate has a 2 minus charge, right? And so what we're going to see is, of course, the sort of very same thing that we had when we added HX across this. What we're going to see is, of course, this area of electron density going and attacking this mercury that's right here. And so if we go ahead and draw that, again, what we're going to note is, just like the last time, this is going to put the carbocation that you're going to form. And again, remember, we're going to form this secondary, secondary vanillic carbocation right there. And right here is where we're going to have our mercury sulfate hanging on. And the next step is now our nucleophile. Remember, we're doing this in sulfuric acid and water, so we have lots of water that's hanging around. So the next step is to have our nucleophile come in, which is going to be our water. And it's going to attack, of course, our carbocation. I'm just going to draw this guy right down here. So let's just kind of turn the arrow down a little bit. And what we can see is we now have our product. That should be SO4 over there. And we now have a plus charge that's on this guy. Water can come back and get rid of that charge by picking up the extra hydrogen that's there. And we now form our product. We still have a little bit of the mercury that's on there. And so treatment with a little bit more acid gets rid of this. Remember, we just have formed some more acid right here, right, by this H3O plus. So I'm just going to write H plus right here. Treatment with some more acid removes then your mercury that was attached, and now we have this new product. Now, there's something special about this product, and that's the fact that this is what you call an enol. And it's an ene because of the double bond, and then of course all because of the alcohol that we have here. Right, so this is what you refer to as an enol. Now enols undergo something which is called tautomerism, and we'll talk about that in just a minute, except for the fact that you should note that the equilibrium between for a tautomer, which is what in each individual piece is called, this enol lies in the form of the ketone, and so we should just draw this. So like so your final product actually that you end up with is actually the ketone here. This is the final product that you end up with. Okay, so the next reaction is again another hydration reaction, and this one, just like with alkenes, we also can add a borane to our alkyne. So in this case, let's look at an example. We'll use our same boring old alkyne that we've had. So here is this guy again, and in this one we're going to add now a borane. So this will be BH3 in THF, and our intermediate that we're going to get is going to add just in the same fashion as it added to alkenes. And so our intermediate is going to get us to this guy right here. And what you need to remember is that because we have 3 hydrogens on this borane right here, it adds 3 times. And so once again, we're going to use hydrogen peroxide, H2O2, and OH minus to give us our final product, which in this case is going to be this enol that is over here. And so we again get an enol. Notice though that this one puts the OH on the least substituted carbon. So here we have OH least substituted carbon, just like we did with alkenes. So this again will add just in the same fashion as it did with alkenes. So if we look down here, what we can see is that we have this guy, our alkyne, and we have our borane. And this guy is going to go here, which then pushes this one over here, and we end up with our intermediate and remember we already had a hydrogen there. And then this one, since we have two more hydrogens, can do the same exact thing again until all of these hydrogens are gone. So it's going to repeat this process until all of the hydrogens are gone, and you end up with something that looks like this, where you have replaced all of your hydrogens. So all H's are replaced here at this one. You're only left with the borane, and this is all you end up with. Now, the next thing that we have to note is, of course, as we discussed in the last one, this is not your final product. Your final product is going to be a tautomerism, and so you end up, if your alkyne is a terminal alkyne, i.e. at the end, you're going to end up with this aldehyde as your final product. So if your alkyne is terminal, meaning an ending, or on the end, then you get an aldehyde. And if your alkyne is internal, in other words, inside the chain somewhere, then you also get the ketone. Here, just like you did with the oxymercuration reaction. So this, again, is hydration. This is hydroboration / oxidation, where we end up with this species. The tautomerism that we've been mentioning, and what happens here. So the tautomerism that occurs, so Ta, that should be an A, reaction here that occurs. And so basically what we said is that the equilibrium in this is going to lie towards the aldehyde or ketone in this case. And so essentially, if you were to look at a tautomer or the individual pieces, we can draw something that might look like this. Where we have the OH here, and we have this guy that's right there, and we can go towards this direction. We have this equilibrium that is in there, and if we add just a little bit of acid, this can be acid or base catalyzed as far as what's going on here. And what we can see is that we indeed end up with the greater part of the equilibrium lying on the side of the carbonyl. So basically we don't really have any of this guy going in this direction. It's way much bigger in this direction here. And so what's happening here, if we just look at a mechanism in this case, right, so we can see that we have now our carbonyl, or our alcohol, our enol. So here is our enol. This is what you call the enol tautomer. And we're going to add a little bit of H plus to this. So a little bit of acid over here. And the first thing that's going to happen is these lone pairs that are right here on this oxygen are going to kick down to form the ketone, or aldehyde in this case, form our carbonyl. And then these are going to force over here to pick up this extra hydrogen, this proton that's right there. And so now what you can see is that we have something that looks like this. And the next thing that's going to happen is, of course, water is going to come back in again, and we're going to regenerate our acid that we had, and we have now our final product. This happens, like I said, with both aldehydes and ketones, and it happens in this case, we did it under acid conditions. It can also happen under basic conditions. And so if we draw the process here for a base catalyzed phenol reaction, so here is now our OH minus, and what's going to happen in this case is this is going to deprotonate our enol, putting charge on the oxygen, so we have our intermediate right here. And we're going to reform this base with water that is we have in solution. And so the next thing that's going to happen is these are going to kick down to form the carbonyl. This is going to go over here, and we end up getting our keto form of what was our enol. So these are the steps for tautomerism in either acid or basic condition. So the next set of reactions that we need to talk about for alkynes is, of course, reducing them all the way down to either the alkene or the alkane. And so we can refer to this as hydrogenation. And so just like when we did the reactions with alkenes, we can use hydrogen with palladium on carbon, so hydrogen gas with palladium deposited on carbon to give us a reduction all the way down to the alkane. And so an example of this would be, for instance, if we take our same old friend right here that we've been using, treatment of this with hydrogen gas and palladium on carbon. And typically this is done in an alcoholic solvent, so something like ethanol, ETOH for the abbreviated for ethanol. And what we can see is that we end up with CH3, CH2, CH3. We've completely reduced the alkyne all the way down to the alkane. So we get complete reduction. Another reaction that we can use to do this, if we don't want the alkane but we want the alkene, we have to do a couple of different things. So if you want the alkene, you have to do something called poison the catalyst, or go about it in a completely different way. So the way to do this to get to the alkene is to use what is called Lindlar's catalyst. And when you use Lindlar's catalyst, you simply just want to write your compound. So here is our alkyne, and you're just going to write H2 gas and Lindlar. And we notice here in this case that we end up getting a cis alkene, as both of the hydrogens now are going to add for on the same face. Now in this one, of course, you can't get, you're not going to get cis or anything because we have these guys, but what we would note if we had an R group here, we would have these two hydrogens on the same face. So the Lindlar's catalyst is simply a palladium deposited on something like potassium carbonate, and then it's poisoned with either some sulfur compounds or lead. And so it basically takes away the activity of the catalyst and lets it stop at the alkene. And so with Lindlar's catalyst, we end up getting the cis alkene. All right, so now if we want to get a trans alkene, we have another option available to us, and that is using a lithium and ammonia reduction, which this is also often referred to as liquid electron. And so to get the trans alkene, we are going to use lithium and ammonia. This is actually a really pretty reaction because this turns a nice deep blue color when you mix the two together. It's very interesting to watch. And so what is going to happen here is I'm going to first, let's just draw our hand that we've been using. And we're going to treat this with lithium. Now we know that lithium is a metal, and so metals typically want to give up their electrons. And so what's going to happen in this case is that lithium is going to give up one electron. And we're going to note this with a fishhook or a half arrow, like so, which then is now going to force these electrons over to the next carbon. Now, what you can see from this, and if we look at this and draw this intermediate, is that these are going to happen on opposite sides. So here is this guy right here with the electron that's up there. Our minus charge is down here at the bottom. So now we have a minus charge that is across. It wants to get as far away from as possible from this electron that's right there. And so here we have now our ammonia that's coming in, and what we can end up doing is deprotonating one of these, and this picks up one hydrogen from there. And so we can see that we have our product. And we still have this radical that's hanging out right there. And so now the next thing that can happen is lithium itself can donate another electron. Lithium is going to add here one more electron to give us a full minus charge. And this is then going to pick up another hydrogen from our ammonia that we have in solution. And I'm going to draw this one in green. These are the two hydrogens now that we've added to this. this one blue. And so notice that these guys are on opposite sides of our double bond. Right? This one is up, and then this one over here is down. So lithium and ammonia gives us trans alkenes. Set of reactions are what we refer to as, just like with alkenes, we can cleave them with potassium permanganate or ozone via ozonolysis. We can also cleave alkynes. We can cleave them with the same two. So we're going to write this as oxidative cleavage. And really the only two major things that you need to focus on for this are whether the alkyne is either an internal alkyne or a terminal alkyne. And so if it is an internal alkyne, let's say we can draw something that looks like this. And we're going to react this over here with potassium permanganate, so KMNO4, or we're going to use ozonolysis, so O3. And you should know that your products are going to be two different carboxylic acids. So one will be from one side of the alkyne, and the other will be from the other side of the alkyne. And so you can use this kind of nicely here to figure out what the original alkyne was if you just simply put these two guys together where the carboxylic acid is. So in this case, all you're going to do is you're going to cleave right down the center of this guy, and you're going to put a carboxylic acid on that one, and then put a carboxylic acid on that one, and therein is your product. Now, if it is a terminal alkyne, meaning on the end, then what you can see is that you end up with one carboxylic acid, and you end up with a molecule of CO2. So oxidative cleavage with, again, potassium permanganate, or we can use ozonolysis. It gives us one carboxylic acid that's going to be from this portion of it. So we end up with this carboxylic acid. And then the other portion of it, we end up with CO2, which you can imagine will bubble out of solution because this is a gas. And so this one gives you the carboxylic acid. And then I'll put this one over here in red. This section right here is due to the CO2. And we can see again that we're simply going to cleave right down the center of this alkyne. So this half, you just take this guy right here and stick a carboxylic acid on it. This one you just draw as CO2. Okay, so the last set of reactions for alkynes refers to their acidity. So it turns out that alkynes are slightly acidic. They have a pKa value of around 25. Okay, and so we can take a really strong base and we can deprotonate an alkyne. So alkynes are somewhat acidic because they have a larger amount of S character. So they're sp hybridized, and so S orbitals are closer to the nucleus, which is positively charged. And so these orbitals are also lower in energy. And so the negative charge can be more stabilized when it's attached to an alkyne. So how you do this essentially is we can take let's take our same old alkyne that we've been working with, and we're going to treat this with a very strong base. And so something like sodium amide is preferable. And so what's going to happen here is the negatively charged base here is going to come and pick up this proton, and it's going to put the minus charge there onto the carbon. And so this gives you this minus charge. And now you can react this with some electrophile. So an example would be like iodomethane, so CH3I. And you can actually extend the carbon chain by 1 in this case. So here we have our alkyne that we've now extended by 1 carbon. We've added this guy right here to it. So we can actually do this with this strong base, and so what you form is this guy, and this would be your acetylide anion. This is not really an acetylene. Acetylene is, remember, the simplest alkyne, which is this guy. And so this is acetylene. And if you deprotonate this, you end up with the acetylide anion. Which looks, again, just like what we talked about. So your acetylide anion. Should be an I right there. So here you have your acetylide anion, and this is somewhat nucleophilic. Now, there are some limitations to this, and this is really only useful, so let's just make a note. Limitations with this. And so you're limited to primary alkyl halides. In this case, so the fact that these acetylide anions are strong bases, you also can undergo elimination reactions if you have secondary or tertiary alkyl halides. So undergo elimination reactions when secondary or tertiary alkyl halides are there. So for example, let me just draw a line right here. If we have this alkyl halide and we treat this with an acetylide anion, what ends up happening, instead of getting the substitution product that you want, like this one up top right here, you end up actually eliminating hydrogen from this, or eliminating HBr, and you don't get the product that you would desire. So this would be your major product, as opposed to chain extension.